Welcome back to the Packet Lab. Today we're going to take a look at another in the OSPF series. Today we're going to take a look at OSPF parameter mismatches. Okay, before we get started on this lesson, I'm not going to go deep dive into a lot of this stuff. I'm going to assume that you know some of the basics here, such as the OSPF network types, the hellos, and how to configure those. There are separate lessons on all of those topics. So if you haven't viewed those, go back and view them. You're going to get most of this. You won't have to go too deep into this, but it's probably better if you understand how to change those parameters. I'm not going to go too deep into, the IP OSPF dead interval command and how to configure that. I'm going to assume that you know how to configure that. Also, you're going to need to have a decent working overview of OSPF. You don't have to be an OSPF guru, but you're going to need to know how some of this stuff fits together. What an area is, why interfaces have to be in the same area, blah, blah, blah. Okay, with that caveat out of the way, let's get into the actual lesson. So in order for an OSPF neighbor relationship and then consequently an adjacency to form, there's a number of values / parameters that must match between the potential neighbors. And it says here these values are carried in the OSPF Hello packets. A lot of them are, not all of them, as we'll see. And they're exchanged between the devices on the network link. And we've covered these in other lessons. Like I said, go back and view those lessons if you haven't seen them already. And what we're going to do in this lesson is we're going to concentrate on the common problems with bringing up OSPF neighbors, getting that adjacency established so that you're exchanging routes back and forth. And these are the OSPF parameters we're going to take a look at, these mismatches. So when you're looking at this, the ones that must match, these first 6 here, is the HelloInterval and the RouterDeadInterval, and then the area. And then authentication really has 2 parts. It's method and password. Obviously, both of those must match for this to work. Stub flag, without going into a whole lot of detail, stub flag is when you agree that an area is going to be a stub area. And if you don't know what a stub area is, again, go back and check out that lesson. But all routers within a stub area have to agree. So they have to have their stub flag set. And then MTU, that's kind of a strange one that catches a lot of people off guard, but that's the maximum transmission unit. So then next up is the network type, and that must be compatible. Now notice I didn't put that under must match. It must be compatible. And we'll go into what compatibility looks like when we're talking about OSPF network types. And then the router ID has to be unique. And then the last one here is a network mask, and that one must match sometimes. And we'll take a look at when it must match and when we really don't give a damn. And here's our OSPF Hello packet. And if you've watched the lesson on OSPF Hello, then you will have seen this. You'll actually have seen this in quite a few of the lessons here. And you can see that the fields that are in here, some of these are the guys that we have to match on, such as network mask, HelloInterval, RouterDeadInterval, designated router, and backup designated router. Kinda that'll come into play when we talk about compatible OSPF network types, and then the rest we're not too concerned about that. But a lot of these parameters are exchanged in the OSPF Hello packet and must match for a neighbor relationship to come up. And real quick, neighbor relationship is when the neighbors say, hey, I agree that I want to be your neighbor and I'm cool with all the parameters, we match on these, so let's start exchanging routes. And adjacency is actually after the routes, and in this case routes are actually LSAs, have been exchanged between the 2 OSPF neighbors. So there's a subtle but important difference between that, and a lot of people tend to say adjacency and neighbor relationship interchangeably. I'll probably end up doing that quite a few times over these lessons, but there is a distinct and important difference between those 2 conditions. So let's jump into our first mismatch, and that's going to be the area mismatch. And from this diagram, you can see it's pretty easy to see that we have a problem here. If you are aware of the importance of areas within OSPF, you know that interfaces on both sides of an OSPF link have to be in the same area. In this case, we've got R1 is in area 1 and R2 is in area 2. So they're going to have an area mismatch, and that means they're not going to establish a neighbor relationship between those 2 devices. And of all the OSPF mismatches we're going to take a look at today, this is probably the most common, simply because fat fingering usually is the culprit here. Could be poor design, but generally it's, you meant to type in area 1 and you typed in area 11 instead. So OSPF neighbors must belong to the same area or they will not form a neighbor adjacency. Okay, I just kind of combined those 2 terms there. They won't form a neighbor relationship and subsequently will not form an adjacency. I'll have to fix that slide. Anyways, let's take a look here. So R1, we can see that we have the link between the 2 devices, which is going to be the 10.1.12.0/24, the serial link between R1 and R2. We can see that that has been assigned to OSPF area 1. Whereas if we jump on over to R2 here, we can see a little different configuration, but all of the interfaces on R2 have been assigned to area 2, which includes the 10.1.12.2 interface, which is the series 0/0. Show IP OSPF interface brief is your friend. It's one of my favorite OSPF show commands. It's one of the ones I use probably the most, that and show IP OSPF neighbors. So it gives you exactly what it says. It shows you the OSPF characteristics of an interface, but just brief, just the stuff that you really need here. And in this case, if I want R1, we can see that we are in area 1, and we issue the same command on R2, and our serial link is in area 2. Therefore, we have an area mismatch. So when we issue the show IP OSPF neighbor command, we don't get any output, and this wouldn't matter if we did it on R1 or R2. It's going to give us the same thing. So the frustrating bit with this is that, like I said, it's pretty easy to do this. You fat finger the area number and you end up with this area mismatch. Frustrating thing is iOS is not going to give you, fireworks or say, warning, you just screwed up. It's really not going to tell you anything at all. And I'm not going to do a separate lab lesson for this. This is going to be kind of a long lesson. I'm just going to integrate that in there, and we'll get on the CLI in just a bit here. I want to show you these commands, but I'll show you when we're on there that you don't get log messages on this. You just don't have a neighbor come up. So short of doing a packet capture, the next best thing that you could do is to debug. And I'll give my standard warning here. Don't do any debugs on production gear unless you have permission from the monkeys above you and you know what that's going to do to your Cisco device, because you can turn this into a career limiting decision. So if you're in the NOC or you're just deciding to check out some cool debugs, do it on lab equipment. Don't do it on production equipment. You have been warned. I will show you, and I'll save that towards the end. I'll have to write this down to remember, is that there's a way to limit your debug so it's only on a specific interface. So in the labs here, it's not going to be that big of a deal because we're going to have generally just single connections, a couple routers, single connection, just to illustrate this. But in the quote-unquote real world, you might be on a core router that has, 5, 10, 50 OSPF neighbors, tons of interfaces. So if you were to issue one of these debug commands, you're going to get that debugging for all the interfaces, and a lot of times you just want it for a specific interface. So I'll show you how to limit that towards the end, so that will help you out with your troubleshooting. But the commands that we're going to use are going to be debug, IP, OSPF, and ADJ stands for adjacency, and you can see that here. It says OSPF adjacency events debugging is on. I won't go out on a limb and say all, but the vast majority of OSPF debugs start with debug IP OSPF. So you can see here that we got this message that says receive packet from 10.1.12.2 and then the interface, and then it says area 0.0.0.1. What the hell is that? Well, that's the area. And I'll show you in a different lesson here, but this is the area displayed in octet form. So luckily we're using pretty easy ones here. It's .1 and .2. So that's area 1 and area 2. It gets interesting when you start getting areas over 255 when you fill up that last octet because it doesn't translate it for you. So again, that's in a different lesson, kind of a little trivia off topic type thing. But anyways, what we're seeing here is that area 1, and then we're seeing mismatch area 2 in the header. So this is a received packet, so in the header means the packet that we've received, and we're receiving it from router 2. So basically what we can see from this is that router 2 is saying, I'm in area 2. And we're saying, no, I am in area 1 for this interface. So we have our area mismatch. You can also run debug IP OSPF events. Gives you a little bit more here. It shows the hellos going back and forth, but either one works. Debug IP OSPF adjacency is probably the better one here because you're going to get the information that you need. You don't really need to know that hellos are going back and forth unless that's part of your troubleshooting as well. So generally when we're troubleshooting this, we're going to just take a look at our running configuration and or our show IP OSPF interfaces. And when you see a neighbor relationship that should be up, or you believe that it should be up, this is one of the first things you want to check, is to see whether or not you've got the area configured right. Now, where these debugs come in handy is when you're trying to create a neighbor relationship with a router that you don't manage. It could be a third party. It could possibly be a carrier, I guess. A lot of times I run into this when we're peering. I shouldn't use the term peering, where we're creating a neighbor relationship with a third party, and you're saying, okay, I want to have this connection be in area 1, and they're like, yep, we got it configured for area 1. It doesn't come up. Well, I can't pop on their router and verify, what area they're in. I can only do that on my side. So this debug comes in handy because they can sit there and say, no, it's configured correctly. I've got it in area 1. Well, this, and you could get a packet capture as well, but that's going a step beyond. this debug will help you out in those situations where you can say, no dude, I'm seeing area 2 in your packet headers. So in order to fix this, we're going to have to change the area on one side or the other. In this case, we're going to go on to R2 and we're going to set this to area 1. So we're going to go into the OSPF routing process. We're going to issue the OSPF network command. In this case, quad 0s followed by quad 255s means all interfaces, and we're going to assign all interfaces on that router to area 1. That includes the interface between R1 and R2, obviously. So then we get a message saying that the area's changed. Yeah, we just did that. We changed it from 2 to 1. And then we get the message that we're looking for, whereas the process is coming up and we're going from loading to full, and we have not only a neighbor relationship in this case, but an adjacency. So this next bit just shows you the running configuration, proves that we put all the interfaces into area 1, and then our good friend show IP OSPF neighbor. On both sides we can see here, and the state is full, and full is good. Full is exactly where we want to be. So then we can also issue our show IP OSPF interface brief, and this is on R1 and R2, and we can see here that those serial interfaces are both in area 1, so we're golden. Okay, so I promised you some dirty hot CLI action, and I'm going to deliver it right now. I've got Terra term on this computer. I thought I had secure CRT, but we will muddle through old school. So here we are on R1. So now let's go ahead and do a show IP type OSPF neighbor, and you can see we do not have a neighbor relationship. If we do a show run section router OSPF, I just do the OS. That's enough for it to figure out what it's looking for. Tick-tock. You can see our configuration here. We have an router ID of quad 1s. Our network, we got the loopback in area 1, and then we also have our serial 0/0 interface in area 1 as well. We just happen to be using 2 separate network commands. Let's go ahead and do a show IP OSPF interface brief. And you can see here that we do have serial 0/0 in area 1. Now let's do a show log. And you can see here nothing in the log, and I'll even go ahead and clear the OSPF process. And you can see no logging. That's the frustrating bit with this, is that sometimes iOS will bug the piss out of you with, you know, your CDP neighbor mismatches and all that type of stuff. But in this case, it will not give you a error message here. So let's pop on over to R2, and we'll just go ahead and show run section router OSPF. And here you can see that we have all the interfaces in area 2, which we can verify with our show IP OSPF interface brief, and there we are in area 2, so we have an area mismatch. And just to prove, I'm going to show IP int brief exclude assigned and ping 10.1.1.2.1. So we do have connectivity. We have layer 3 connectivity between the devices, but we do not have a neighbor relationship. So let's go ahead and pop back on over to R1, and let's do our debug here. So debug IP OSPF question mark, and you can see we have a number of choices here. And as we go through these, we're going to be doing debugs on all of these mismatches, and you're going to find out that there's really just a few that really work well here. We're going to start out with the adjacency, so ADJ. I don't think there's any options with that, so hit enter, and it tells me what type of debugging I have on. That's all we're really going to get from here. I'll leave it up, but I wanted to show you real quick. If I do a show IP OSPF interface S0/0, okay, it's a point-to-point, so our hello intervals, so every 10 seconds we'll be getting something like this. And you can see here that, yeah, 38, 47, well, basically every 10 seconds. I'll just turn off debugging with the UAll, which is short for undebug all. If you have your hello interval set to something higher, you know, if it's one of the defaults is 30 seconds. If you have it set for, you know, some ungodly amount, 10 minutes or whatever, you're going to have to wait for hello packet to be exchanged for this information to come through. But anyways, we can see here the same thing that we saw in the slides, that we're getting a packet from R2 and our area is 1. And sometimes it's hard to read this. You're thinking area 1, okay, it looks like that's saying that it's from the packet, but when we say in the header, that's the packet that we're receiving, and we can see that area 2 is what we have here. So I'll do the other debug real quick here. It's debug IP OSPF events, I believe. Yes. Hit enter, and we're going to get the same thing. So we get the same information, and we should see also, yeah, that's the only additional bit that you get, is that you see that we sent a hello. So we're seeing the packets come in, and we're also logging our hellos that are sent. So I will do a U all to stop that. So in order to fix this, we can do this on either side. We can either put R1's interface into area 2 or do the same thing on router 2 and put that interface into area 1. So let's go ahead and do that. So I'm going to get into configuration mode. I go into the router OSPF process, and it's going to be process 1. And then when I'm doing this, I like to do a show run section router OSPF. Before I make any changes, I like to go ahead and see what the configuration is. Even if I know what it is, I like to check it out to make sure I haven't screwed something up or didn't write something or something's goofy here. And plus it's easier from here to just to do a cut and paste. So what I'm going to do here is I'm just going to take this network command, paste it in, and change the 2 to 1. I'm going to up arrow a couple times. And you can see that my OSPF area has changed, but I also like to go ahead and verify that what I have changed has actually taken effect in the configuration. Because sometimes if you're not familiar with the commands, I might have pasted that in and all of a sudden I've got 2 network commands, both saying, one saying it's in area 1, one in area 2. It's just nice to see how iOS has quote unquote digested this information. And oh, yeah, I kind of screwed this one up. Well, we're getting a little ahead of ourselves here, but let me go ahead and change the router ID here. So just a little preview of another mismatch ahead. I had the router ID set to quad 1s, and that's the same router ID that's on router 1, obviously. So did that on purpose. Let's pop back over to R1, and now let's go ahead and we know it's going to be up here. Oh, we still have our debug on? Interesting. Oh, because, all right. This threw me off because normally you don't see this here, received hello, init, hello, two-way, blah, 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 all this. These are the various states in OSPF when it's forming an adjacency. If we do a show run section router OSPF, and I'm sorry to get off base here. I just want to show you why this was coming up. And the reason is that I threw on this log adjacency changes detail because when I was setting this up, I wanted to make sure that there wasn't a way that you could get the logging to tell you when there was an area mismatch. And even with this on, we didn't see it in the logging. We had to go to the debug. So anywho, let's go ahead and do a show IP OSPF interface brief. And it hasn't changed on this side. We're on area 1. So let's do a show IP OSPF neighbor. Booyah, that's what we're looking for, is full. So now if we do a show IP route, OSPF, we should see that quad 2 is the loopback 0 interface on R2, and we should be able to ping it if everything is cooking with bacon, and we are golden. So the takeaway from this is it's really easy to fat finger and end up with a situation like this where you have an area mismatch. Unfortunately, iOS isn't going to scream at you like it will for some other configuration issues. So you're going to want to start your troubleshooting with verifying that you're in the same area. That should be the first thing that you look at if you don't have a neighbor come up. Otherwise, if you have to go a little deeper, like I said, if you're in a situation where you don't control the other side, you can use those debugs as well. And then the fix, obviously, is just setting one side to match the other. Okay, next up in the OSPF parade of mismatches is the hello/dead timer mismatch. And our topology is going to be ridiculously easy again. R1 connected to R2, and we're going to be in the same area, which is going to be, I guess, area 12 this time, so we don't have to worry about our area mismatch. What we are going to run into is that we're going to have timer mismatches on each side, and I have a lesson devoted exclusively to the hello and dead timers, so that will show you what they do, why they're important, and how to change them. I'm not going to go deep dive into all that stuff here other than to say that they do have to match on each side in order for your neighbor relationship to be established in OSPF. So both the hello interval, which is sometimes referred to as a hello timer, and the router dead interval, which is sometimes referred to as a dead timer, must match in order for a neighbor relationship to be established in OSPF. The keyword there is both. So if you have the hello intervals matching but not the router dead intervals, it's not going to form a neighbor relationship. So here we can see on R1 and R2, the way to take a look at the hello and dead timers is to issue the show IP OSPF interface. Unfortunately, can't use the brief. You do have to specify the interface, or you can just hit enter and I'll show you all the interfaces. But in this case, we're taking a look at 00/0. And you can see here, starting out here, it says timer intervals configured. Hello interval is 6. That means that you have a hello interval of 6 seconds. And dead interval is 24, which obviously is 24 seconds. So we pop on over to the other side and we're taking a look at R2, same interface on R2. And we can see down down here that our hello interval is 10 seconds and our dead interval is 40 seconds. So obviously, even with my American math skills, I can see that those do not match. So we are not going to establish a neighbor relationship on this link until we get those guys to match. So once again, iOS is not going to scream at you and start logging errors that say, you know, there's a hello and or dead timer mismatch between the two potential neighbors. You're basically going to do a show IP OSPF neighbor and you're not going to get any output. So what you want to do is use those commands I just showed you, the show IP OSPF interface, specify the interface on each of the potential neighbors and see if you can find a mismatch. You can also take a look at the running configuration for the interfaces. The interface will have default timers set, and that's either going to be 10 seconds or 30 seconds for the hello, and then 4 times that, which is 40 seconds or 120 seconds for the dead timer. If you see that they're not matched, it's either going to be mismatched network types, or in this case, it's going to be somebody went in underneath the interface and changed the timers. So you could take a look at the running configuration to get that. Generally, I just take a look at the show IP OSPF interface. If you need to, you can also do debugging here. In this case, we're going to take a look at the debug IP OSPF hellos. That's because those timers are carried in the hellos, and you can see here that we turned it on R1, and we see, oh, mismatched hello parameters. Okay. And it says dead R 40, C 24, hello R 10, C 6. Okay, what the hell does that mean? It's actually pretty easy. What R stands for is received, and C stands for configured. So received means this is what the potential neighbor is sending us, and so in this case R2 is the potential neighbor. So it's saying that R2 is saying that its dead interval is 40 seconds, while we say it is 24. And the same thing with the hello, it's saying that R2 says it's 10 seconds while we're saying that it's 6. You can also do the debug IP OSPF events, since basically the only events that are going to be going on at this time is the exchange of hello packets. It's going to give you pretty much the same output. And it says here, note the R versus C. We've already gone through that. You can fix this by changing the hello timer and or dead timer depending where the mismatches are underneath the interface with the IP OSPF Hello interval command or the IP OSPF dead interval command. Remember when I mentioned that you could have different OSPF network types have different default timers? So it could be the case where you could fix this by changing the OSPF network type to match, or to, well, that gets a whole lot deeper. Just keep this in mind that by changing the OSPF network type, you could also change these timers. Generally, that's going to be more of a CCIE lab brain twister type thing. Where the area mismatch is common, this isn't that common. Somebody had to either change the network type or they've been mucking around with the timers, which they probably shouldn't have been. So let's go ahead and take a look at this on the CLI. Okay, so let's go ahead and do a show IP OSPF int brief. And you can see we're in area 12. So let's pop on over to R2 and issue the same command. If we do a show IP OSPF interface brief, we can see that we are in area 12. So we don't have an area mismatch, but if we do a show IP OSPF neighbor, if I can type, you can see that we don't have a neighbor relationship either. So let's, since we're here, do a show IP OSPF interface, and then you can specify the interface. In this case, we're going to look at 00/0. And you see it gives us a ton of good information here. What we're really looking for is the timer intervals here. And if you just want that information, you can always pipe include timers. So you can see here that our hello interval is 10 seconds and our dead interval is 40 seconds. So let's pop on back over to R1 and we'll issue the same command. We'll do a show IP OSPF int 0/0. We'll just take a look at the whole thing, and then I'll show you with the cool piping bit so that we can just concentrate on that. We can see here that our hello interval is 6 seconds and our dead interval is 24 seconds. So we could go to do a show run interface 00/0 and see how that came about. You can see here that some monkey went under here and configured the hello interval to be 6 seconds. Now, by default, when you configure the hello interval, iOS is going to set the dead interval to 4 times that, which is, in this case, 24. Doesn't work the same way in reverse. So if you set the dead interval to, let's say that we change this to 20 seconds, it's not going to set the hello interval to 5 seconds. So that's why we're not seeing a specific line for this dead interval being set to 24 seconds. Anyways, again, I'll pimp out my other lesson on the hello timers, and we go into that in a lot of depth. So in order to fix this, well, I'm getting ahead of myself. Let's go ahead and do a little debug action here. Let's clear the log in case, and debug IP OSPF. And in this case, we want to do hellos. And I don't believe there's any additional, okay. And we shouldn't have to wait that long, between 6 and 10 seconds. So we're sending a hello here. Let's see if we get one back. We should be getting one real quick. Booyah. All right, I'm going to go ahead and yaw this to stop it. And you can see exactly what we saw in the slides here. We received a hello from router 2. It's in router 12, so we know this is an area mismatch. It's telling us what the problem is. It says you've got mismatched hello parameters. And here's the key to the whole problem. Our dead interval is 24 seconds. The received interval is 40. Our configured is 6 for the hello and 10 for the receive. So we have to make those guys match. So we can either go on to R2 and set it to our goofy timers, or we can go back and set ours to normal. Let's go ahead and just show you events. We'll give you the same information. You all. And it's giving us the same information. So you can use either one of those two. I would just go with the hello since that's what we're actually looking at. So now to change this, we're going to go under our interface 00/0. In this case, we can just go ahead and set our OSPF timer. We can either do a no to get rid of that, or we can just go ahead and do, I'll do it this way since it shows you the command, IP OSPF hello interval. And then you can set it to from 1 to 65,000 some seconds. In this case, since we want it to match, we're going to set it to 10. Like I said, if you do a show IP OSPF interface 00/0, and we're just going to include the timers. I've got that stupid detail on there, so you can see that everything's come up in the meantime. You can see here that it set the hello timer to 10 seconds, and then the dead interval to 4 times that. So you can do both. You could specify the dead interval as 40, but you know, we just did it one fell swoop here. So now if we do a show IP OSPF neighbor, we do have a neighbor relationship. We are seeing full. Full is good. If we do a show IP OSPF route, interesting. Oh, that's why. Wrong command. Show IP route OSPF. This is actually looking at something different. It's looking at the database, but never mind. So that's what I wanted. And then ping 2.2.2, and we are good. Yeah, the order of your commands can make a significant difference sometimes and confuse you in the middle of a lesson. All right, so we're golden here. Let's pop back to the slide. Okay, and I have a lesson on OSPF fast hellos. I'm going to go again, deep dive into this. If you're using OSPF fast hellos, the timer does not have to match. And it'll go to this into this in the lesson. It actually is matching. It's saying that the hello interval is 0, but then your hellos are sent out in fractions of a second, which is determined by a local hello multiplier value. If none of this is making sense, definitely go back and check out that lesson. But this is something to take away from it, is that you can have quote-unquote hello timer mismatches here. Because you can see your R1 and R2 both set up for fast hellos. The way you can tell that is the hellos are in milliseconds, whereas normally the lowest hello value you can have is 1 second, and the dead interval will always be 1 second when you're using fast hellos. But you can see here that on R1 we have a hello interval of 200 milliseconds and a hello interval of 333 milliseconds on R2. Yet when we do a show IP OSPF neighbor, we have the full state. Again, we can tell that we're running fast hellos because that dead timer is going to be 1 second. It's going to count down from that. So you're going to actually see this 99.99% of the time in milliseconds. You might get it at I think it'd still be in milliseconds. It would show you 1,000 milliseconds if you happen to get it right when it was refreshing. Not going to go ahead and do this on the CLI. Go back and check out that lesson on fast hellos because we go through this. But this technically is not a mismatch because in the background, it's actually matching on a hello interval of 0. So if you run across this in the real world and you start flipping your wig because you're like, oh my God, we've got a hello interval mismatch, not really. More importantly, a lot of times, if you come across this on a Cisco exam, they may try and fool you with this by showing you this output and saying, hey, has a neighbor relationship been established here? And because it's in milliseconds, you know that you're running fast hellos. And because I just told your ass so, you know that they don't have to match. This is actually a hello multiplier, and the hello interval is 0. So let's move on. Now let's take a look at an MTU mismatch. We're going to use the same simple topology as before. Everything's in area 12, interfaces haven't changed. What's going to happen though is we're going to change the MTU on R100/0 and see what kind of havoc that will wreak. OSPF is going to check whether neighbors are using the same MTU when they're on a common interface. This is going to be checked when the neighbors begin to exchange DBD, which is database descriptor packets. If the received MTU in the DBD packet is higher than the IP MTU configured on the incoming interface, OSPF adjacency will not be established. So you could tell I just chopped that right out of the Cisco documentation because it's worded kind of weird. Basically saying you have to have the MTU match on both sides or it's not going to work. And this is where it comes back to that semantic difference between a neighbor relationship and an adjacency. So like I said, the neighbor relationship is when you agree on certain parameters and say, hey, let's be neighbors. I agree on your hello and dead timers and all this stuff. The second part of that is like, okay, we're neighbors. Now let's start exchanging information. And information in OSPF is going to be these things called LSAs, and it starts sending these OSPF packets back and forth. DBDs are database descriptors. Go into that a little more detail in another lesson, but basically it's the exchange of LSAs at that point, and LSAs equal routes if you just want to simplify this. What's happening here is that MTU does not come into play until that second part, so you'll get a neighbor relationship, but you won't get an adjacency because once they start to exchange these LSAs or attempt to, it's going to fail at that part. So that's where it comes into some interesting behavior, and you will pound your head on the desk because MTU is not something that you commonly think about when you're troubleshooting OSPF. And this will more often happen in the switching world than it will on routers. I'll actually have a separate lesson on this with the switches because there's a couple more commands that you can use in that realm to get around this. The reason it happens there is because you have some technologies that add additional encapsulation like a Q&Q tunneling. So then your MTU size actually has to be bumped up to accommodate that. So when you are going through the switch network, you have to make sure that the switches have the same MTU. And especially when you come out of the switch network into the routed network, I suppose it's all routed, but when you're connected to a router, that's when the fun begins, and you'll see that in CCIE workbooks quite a bit. So let's take a look here. What we've done is we've gone on R1, and obviously we changed the MTU. The MTU is usually 1500 bytes. In this case, it's 666 bytes. It's the MTU of the beast. But you'll notice here, again, when I said that it's not something that comes readily to mind when you're troubleshooting OSPF, the show commands that we're using have nothing to do with OSPF. These are just our basic show interface and show IP interface, and just showing you where the MTU is. It doesn't show up in the show IP OSPF interface because this is something that's on the interface. It's not specific to OSPF. This would be affecting any protocol sent over this interface. So now we go and do our show IP OSPF neighbor, and it's looking good, except remember, we want to see that full, and we've got something called xstart. Well, what the hell is xstart? Xstart is actually exchange start, or basically starting of the exchange of DBD packets. So when you see this, trust me, the first time you run across this in a live network, this will stay with you to look for this. If you see xstart and it's not changing from that, well, it will change. It'll go down eventually. We'll see that in a bit. But usually it's going to be stuck in xstart. First thing you need to do is go look at the MTU because that's generally what your problem is. If not, it's going to be an iOS issue or something goofy that's a whole lot deeper than that. But those are our show commands. That's our neighbor. And here we see we do have a neighbor relationship. We just are not getting an adjacency. All right, I read this top part. It's really just reiterating what I just said, but note that unlike most of the other OSPF parameter mismatches, a neighbor relationship is established when there is an MTU mismatch, and we see that with our show IPS OSPF neighbor. The state shows xstart. This is because the hello packet parameters have been met. Remember that MTU is not included in the hello packet fields, so the neighbor relationship is established. The MTU mismatch rears its ugly head once the two neighbors start exchanging their linked state databases. So when this happens, this phase cannot complete. So it's going to be stuck in this exchange. So you have a neighbor relationship, but not an OSPF adjacency. Remember at the very beginning of this, I said that it's important to keep those words separated. In day-to-day conversation, you usually say adjacency or neighbor and mean the same thing. But this is where that semantic difference comes into effect. So here we are in R2, and we do the same show commands, show interface or show IP interface. And we can see MTU is 1500 bytes, which is normal. And we see that we also see a neighbor relationship, but we're stuck in xstart. And if we were to do a show IP OSPF routes, we would not have any routes from our neighbor because we haven't received any LSAs, so that we can't build our shortest path first tree. And here are debug commands. Let me pull up R1 first because I do want to show you that you will get logging messages here. So I have the MTU mismatch obviously set up here, and you can see that we're getting all of these things. There's quite a bit of time between them. You can see that there's a full minute, 2 minutes here, 1 minute, whatever. It's quite a bit of time, so they're not going to be popping up all the time while you're on the console. But you can see that it's going from xstart to down, and it says ignore timer expired. Neighbor down, too many rate transmissions. Again, once you've run into this in the wild, you might recognize this as, oh, I better check the MTU. But this is kind of cryptic. It doesn't really give us a good feel for what the actual problem is. So in this case, the debugs that we're going to take a look at are going to be debug IP OSPF Hello. And actually, we're not going to look at that. I just threw that on there because it will give you some information. But again, it's going to be every bit as cryptic as those logging messages. It'll show you the too many retransmissions. And then it's going to show you that 00/0 is currently ignored. Well, yeah, we know we got a problem, but that really doesn't tell me what that problem is. If you do the debug IP OSPF adjacency, ADJ, you'll see here that it's going to tell you exactly what the problem is. It's going to say, hey, router 2 has a larger interface MTU. Hey, sweet, you told me what the problem is. Now I got to go fix it. So let's go ahead and take a look at this on the CLI. Okay, so we're on R1. If we do a show IP OSPF neighbor, we see the dreaded xstart. If we do a show log, we will see that those messages have been logging here, but again, they don't tell us a whole lot unless we cut them and paste them into Google, and hopefully somebody's paved the way for us and told us to look at the MTU. So if we do a show IP show IP interface 00/0, it gives you a ton of stuff. What we're looking for though is the MTU, and you can pipe MTU. You can see it's at 666 bytes. Even if you didn't know that was wrong, you'll see that it's different when we pop on over to R2. You can also do show interface, get the same information, and it'll give you a little bit more here. But basically, we've got our MTU set to 666 bytes, and that is wrong in so many ways. So now let's pop on over to R2, scroll up, get rid of that. Same difference, do a show IP OSPF neighbor. We've got the xstart. I'll just show you show IP OSPF interface 00/0, and I'll let you look through that. But basically, pipe for MTU, even the lowercase MTU, or even the MTU, that's all the variations I'm going to try. You'll see that it doesn't show the MTU. The MTU is not specific to OSPF, so it does not show up here. But if I do a show IP int 00/0, and I'm just going to include the MTU, we see it's 1500 bytes. Same thing if I decide to save myself a couple of characters and not type the IP, 1500 bytes. So we have a different MTU size on R2 than what we have on R1. So let's go ahead and pop back over to R1 and do our debug. We're going to do a debug. Let me clear the log first, because this stuff does show, this does pop out quite a bit of stuff. So clear, okay. So I do a debug IP OSPF, and do you remember which ones it was? Well, we could do hello, but that's going to give us some cryptic bullshit, and we want to be on the right path. So we're going to do adjacency if we can type it right. And by we, I mean me and my fat fingers. We've got adjacency on, and we might have to wait a little bit here to get the message. Nope, there we go. All right, I'm going to shut off the debugging with my y'all. So you can see here, we got it a couple times here. We didn't have to wait too long for it. Number 2.2.2.2, so that's the R2's router ID, has a larger interface MTU. So now we know what the problem is. And it's actually kind of cool because it shows you what the MTU is. So if you had, like I said, if you didn't have access to the router on the other side, you could say, hey, you've got your MTU cranked up. It's bigger than mine. I won't touch that. I can tell you that you don't fill me full of crap, because I can see the MTU in this packet is 1500. So let's pop on over to the slides and see how we can fix this. Before we do this, I'm not going to do this on the CLI because you have to wait a long ass time for this to work. But if you go ahead and debug IP OSPF events, you'll see this stuff coming through, and this is where we get that cryptic message, that we get in our log, just normally without any debugging, that it's going to give you that excessive retransmissions. What's happening is it's going through and it's sending out a DBD, which is a database descriptor. It's saying, okay, well, it sends one. It says, all right, I'm going to send you a DBD, and then it's going to say, okay, well, you didn't seem to like that. Let me go ahead and retransmit that. So it keeps sending out this DBD to R2, and you can see here that these increment, and I obviously cut out a whole bunch of this. Gets up to about the 25th attempt, and it says, you know what, that's enough of this garbage. I'm going to go ahead and kill this. Well, what it does is it just basically restarts the process, and you go into xstart again, and it'll send out another 25 and keep doing that and fill up your router log. But this is where that excessive retransmissions message comes from. Maybe it's not as cryptic to the router, but it's kind of cryptic to us because it doesn't say, hey, check the MTU. So there are two methods to fix the MTU mismatches, and actually I'm lying to you right now because it depends on what type of device and the iOS code. There can actually be more than two. I'll explain that in just a bit, but the easiest thing is to go ahead and set the MTU to the same size on both sides of the link. So in this case, we shouldn't have our MTU set to 666, so we go over to R1 and we set it to 1500. And we're golden because it matches on both sides. Now, if there is a reason why the MTU is mismatched, and like I said, on switches, you might have bigger MTUs because you have a Q and Q tunneling or something like that, then you can go ahead on the device with the smaller MTU and bump that up. Or what you could do, and this is probably the better way to go, is use an OSPF specific command. It's IP OSPF MTU ignore, and you use that on the interface. Now, I've been told that you use it on the interface with the smaller MTU, and we'll actually test that guy out on the CLI. Put it on both sides here. I don't think that affects anything if you put it on both sides, but supposedly you only have to put it on one side, and that's the one with the smaller MTU. And it's going to basically say, you know what, when we get to the point where we're going to start exchanging our LSAs, let's just don't worry about this MTU garbage. I don't care about it. Just give me your information and you'll be good to go. They said there's more than two ways on some switches. And like I said, there's going to be a separate lesson specific to MTU mismatch on switches. You can set the MTU for routing to a different size than your interface MTU. Watch that lesson. That'll show that in better detail. But basically what it's saying is like, okay, for routing protocols, I want this MTU to be, 1508 bytes. But my normal interface, I want it to be 1500. So it gives you some more options to quote unquote fix this. Usually though, if you're in the OSPF realm, that IP OSPF MTU ignore is probably the best route to go. And actually, let's pop over to the CLI and see how that guy works. Okay, let's do show IP int 0/0/0, include the MTU. And so now if you remember, well, there it is. Well, not quite black and white, yellow and blue. Whatever. This side is smaller. This side has an MTU size of 666 bytes, while R2 has a MTU size of 1500 bytes. So let's go ahead and get into configuration mode. And this will actually be under the interface. So you go into the interface. In this case, it's 00/0 IP OSPF, which is what we use for almost all of our, if not all, of our OSPF interface commands. And what we're looking for here is that MTU ignore. And I don't think there's any options with it. So let's go ahead and hit enter here and see what happens, because I've been, well, booyah. Okay, so whoever said that was correct. I went and changed it on the side with the smaller MTU, and if we do a show IP OSPF neighbor now, we can see that we have a full state, which is great. That's hella better than xstart. And I'm guessing that if we pop over here, we'll do the same thing. Yes, and if I do a show int as 0/0 include MTU, you can see that our MTU is still bigger on this side. So I just fixed it on that side. Let's go ahead and remove that. See if it matters. Okay, so it is down. So now I've cleared that command. I want to pop over here on the side with the larger MTU and IP OSPF MTU ignore. And let's see. Yeah, I don't want to sit there. This is those retransmissions. So it looks like it's not working when you do that. So it seems like it's right. All right, so for future reference, if you want to minimize your configuration, you only need to put the IP OSPF MTU ignore command on the side that has the lower MTU. You can put it on both though, so let's just jump back over to R1 and do that. Yeah. Okay, there's an additional caveat with the MTU. If you have an OSPF neighbor adjacency, and neighbor adjacency just basically means adjacency, established, and you change the MTU, it's not going to affect the adjacency until it's reset. Now that could be reset by bouncing the interface or doing the clear IP OSPF process. And I have an asterisk here, and I think we'll test this out. Because the problem doesn't rear its ugly head, as I stated earlier, with the MTU, until you get to the database exchange, the LSA exchange, my guess is that when that happens, and that gets triggered on default every 30 minutes, because normally LSAs aren't being exchanged unless there are changes to your OSPF topology. That's one of the benefits of OSPF. It's not sending out stuff all the time. It sends out hello messages all the time, and that's just a keep alive mechanism. But as far as the routing, it's not going to keep spitting out routing, so it's a pretty quiet protocol. Yeah, here we are, we're on R1. We change the MTU to 666. We see that that's different from R2. We do show IP OSPF neighbor. Now, obviously, we had OSPF running before this, and there's no change. It doesn't drop because of the MTU. But when we clear the process, then we get the xstart back, which is a dreaded xstart. Let's go over the CLI and test this out. All right, so let's go ahead and do a show IP in test 0/0, include MTU, and it's 1500 bytes. I'm actually going to copy this so you don't have to watch me painfully type this. Pop over to R2, do the same thing. So we've got the MTU set to the same value on both sides. If I do a show IP OSPF neighbor, you can see that we do have an adjacency established. If we do a show IP route OSPF, and I can ping that one. I've got an OSPF route. It's the only OSPF route I have, and that is to the loopback of R1. So we're golden right now. So let's go ahead and, since we already did it on R1, let's pop over there and go into configuration mode, go into the interface, and change the MTU to the MTU of the neighbor of the beast. So now if I up arrow, I should be able to see my MTU has been set to 667 bytes. But if I do a show IP OSPF neighbor, I've still got the neighbor relationship. I've got the adjacency because if I do a show IP route OSPF and ping 2.2.2, you can see that we do have an adjacency. So changing the MTU is not going to affect it until this until this OSPF relationship is reset. Like I said, that can be the interface going down, that can be clearing the process, that can unfortunately be the router reloading. So if this happens, you're like, oh, okay, I changed the MTU. Maybe you had a legitimate reason for doing this, and then you walk away. Well, the next time this router gets reloaded, it's going to clear that process, and that's going to break this. Now you've got the too many retransmissions, and you're like, what the hell's going on here? And like I said, until you see this in the wild for the first time, you're generally not going to jump to MTU being the issue. What I want to test here, though, is because the problem occurs when they're exchanging the LSAs, and right now no LSAs are being exchanged. There was an initial exchange. Nothing's changed here. It won't change again until, I'd have to look it up, I think 30 minutes. There's an automatic triggered update where they time out, and you could disable that as well. So let's go ahead and make this easy. If we do a show run section router OSPF, if I have this set up the way that I think I do, it's going to put all the interfaces on this router under into area 12. So simply adding a loopback here. I want to configure the terminal. I put interface loopback to IP address 11.11.11.11.255.255. Exciting. So what I'm doing is I'm adding a loopback address to R1, which is going to add a route into OSPF, which means for that route to get over to R2, LSAs have to be exchanged. But now with the MTU mismatch, will the LSAs be exchanged? Will this break now? Will we go into xstart now? I'm thinking yes, but honestly, this is the first time I've done this. I don't know. So let's go ahead and see what happens. Nothing exciting so far. Our neighbor relationship is still full. Let me jump over to R2. Yep. Well, here's the proof in the pudding. If we do a show IP route OSPF, and if we see that quad 11s, and we do, and it works. Okay, so I was wrong. So this is actually even more devious because you won't see it until you do something like this. Clear IP OSPF process. Say yes. It's going to take it down. Now let's do a show IP OSPF neighbor. And we're back to xstart. And we're going to see the same thing on the other side. Let's see if we still got our debug in here. And we'll wait just a second. I might pause this. Nope, there we go. And you can see we're back to this MTU mismatch. So yeah, that can be devious. If you go ahead and change it, or for whatever reason the interface gets changed, it doesn't break it right away. It will break it when the process is reset, which is similar to the router ID being unique. See that when we get to that section. But yeah, that can be ugly because it might be months later that this gets reset, you know, through a power outage, or the interface bounces or whatever. So yeah, can be ugly. Point made. Let's move on. Next up is authentication mismatch, and it's really not that hard to get your head around this. You don't have to be an OSPF guru to understand how authentication has to match on both sides in order for it to work. So we're going to use the same topology that we've been using, nothing special here. OSPF is going to support 3 different authentication methods, type 0, 1, and 2. Type 0 is null authentication, which, kind of like it says, there's no authentication going on. Technically a form of authentication, but that form is no authentication, if that makes any sense. I've heard it described as kind of like not getting a raise, but your boss tries to present it in the best possible light and says, oh, you're getting a raise of 0%. So in this case, yes, you have authentication. That authentication type is no authentication. Moving on, plain text authentication is type 1, and that's exactly what it says. It's going to use authentication, but the passwords are going to be in clear text. MD5 authentication, which is type 2, is going to use MD5 cryptographic passwords, so an MD5 hash for the password. So they go in ascending order of strength. So what this really means is that we're going to have 2 different potential types of authentication mismatches. We're going to have a mismatch between the authentication type and then the old school plain Jane password mismatch. So if we agree on a type, we also have to make sure that our passwords agree as well. So looking at the authentication type mismatch first, R1 we've got configured to use MD5, which is type 2. R2 is not using any authentication at all, which is actually type 0. Like I said, kind of weird. So show commands, it's going to depend on how authentication has been set up in OSPF. And let me briefly explain that. There is a lesson dedicated completely and utterly to authentication. I strongly suggest you check that out. But basically, just as a reminder, OSPF can set up authentication on an area basis, which means if you set it up for, like, say in this case area 12, then all interfaces within that area have to have authentication set up. Or you can set it up on a link by link basis, which, you know, in this case, let's say area 12, but we only want to have the link between R3 and R4 be authenticated. So you can set it up either way. So depending on how it's set up, that what the show command is going to give you, you can always do the show IP OSPF interface command. If authentication is set up and it's not type 0, it's going to show up there, regardless if it's on just the link or if it's on the area. So we issue that on R1, gives you a bunch of stuff. You get down to the bottom there, it says message digest authentication enabled. So that's MD5, and we know because we just watched the last slide that that is type 2, and we're not going to worry about the keys. Unfortunately, type 0 doesn't show up. It's a default. It's not really doing anything. So if you issue the show IP OSPF interface and it's running type 0, you won't get anything. So you know which type of authentication it is simply by the fact that it's not showing you any authentication. So that's type 0. So now if we do a show IP OSPF neighbor, obviously we're not going to get a neighbor relationship because we're not even agreeing on the authentication type. So now if authentication has been turned on an area basis instead of just on a link by link, if you do the show IP OSPF command, it will eventually, there's a ton of stuff that pops up here, show you whether or not an area has authentication enabled, and if so, what type. So we see on R1, if we issue that command, that eventually we get down to area 12. And remember, there could be multiple areas on the router if it's an ABR. But we can see here that that area has message digest authentication, which is MD5, which is type 2. We do the same thing over on R2. In this case, it does show that there is no authentication going on. So area 12 has no authentication going on, which means it is using type 0. So we want to troubleshoot this. We're going to go ahead and use our handy debugs, and we're going to look at debug IP OSPF adjacency. You can use events. It's going to give you a little bit more information, nothing that's really important. So I would just stick with debug IP OSPF adjacencies. And you can see here that we get a message that says that we've received a packet from 10.1.12.2, which is router 2 on 00/0, and it tells us in plain old English that we have a mismatch of the authentication type. The input packet specified type 0, we use type 2. So we're getting type 0 from R2 and we're using type 2. So this is where that knowing the type kind of comes in handy, because there's a little bit of reverse engineering in this debug message. So you know that they're not using authentication whatsoever, because we know that type 0 is null authentication, whereas we're using MD5. Quick look at the running configuration would figure that out for you as well. But we have found our problem here. So let's go ahead and take a look at this on the CLI. All right, so let's do a show IP OSPF neighbor. And you can see that we do not have a neighbor relationship. Show log. I don't know if I cleared it from last time. I did not. You can see that there's no messages in the log that say that we have an OSPF authentication mismatch. Do a show IP OSPF interface 00/0. We can see here right down at the bottom it says that message digest authentication is enabled, so that's MD5 or type 2. Pop on over to R2, show IP OSPF neighbor. Of course, we're not going to have neighbor here. Show log. I don't know if I cleared the log here either. No, but there's nothing new in there that shows anything that has to do with authentication mismatches. Let's go ahead and clear the log. And then if I do a show IP OSPF int 00/0, nothing fun here because it doesn't tell us anything about authentication, which we now know means that we are using type 0. So we have an authentication type mismatch. We can also do a show IP OSPF, and I told you this gives you a ton of stuff. Look at how much stuff comes out, and this is a really simple setup. We just have one area, really one interface. So if you got an ABR cooking with a ton of different areas, you can see that this can get pretty deep pretty fast. But what we're looking here is under the area, and we only have one area, which is 12. Area has message digest authentication. So we've actually turned on MD5 authentication for the whole area rather than just on a link by link basis. And if I do the same thing over on R2, you can see down here, oops, sorry, I'm working on this laptop and I've got the nub instead of the mouse, and my mouse just went crazy on me. What the hell? Okay, well, down here where it says area has no authentication, I would have loved to highlight that for you, but there's my mouse. Okay, area 12 has no authentication, so we see that we have an authentication mismatch. Let's go on over to R1 and we're going to do a debug IP OSPF adjacency. And let's see how long it takes for this to cook. Yeah, we know that we sent it with a key. Come on, there we go. So just like in the slides, I have not lied to you. You see that we got a packet from R2 on 00/0, and we have a mismatch authentication type. They are using type 0, which means no authentication whatsoever, and we are using type 2. So we can fix this. What we're actually going to do though is take a look at the second potential broken part. So what we'll do is we'll match the authentication types, and again, I'm not going to get into the configuration of that. There's a separate lesson for that, but we'll go to the second bit where we have the authentication types matching, but we don't have matching passwords, and see what the difference is with that. Now, okay, before we get to that, we'll have another authentication mismatch. We're not going to do this in the CLI, but here I've set R2 to have type 1, simple authentication, clear text, whereas R1 is still using type 2 or MD5. So if we do a show IP OSPF interface 00/0 on R2, we can see here now that we do have authentication enabled, whereas before it wouldn't show us anything because we had type 0 or null authentication. Now we're using the type 1 simple authentication, and simple password authentication is enabled. So now if I go ahead and do that same debug, you can see we get the same message, except that now input packet specified type 1, which is clear text, and we are using type 2, which is MD5. And actually that can be a big problem. A lot of times that will happen where you have clear text on one side and MD5 on another, and it can get really goofy. But so it's good to know this. Again, you can go ahead and check with the show commands on either side to see how your authentication set up. I'm not going to go ahead and do this because there's another lesson that goes into authentication. So let's move on. Right, so now we're on to our second type of mismatch, which is a mismatch of the password itself. So R1 and R2 are both set up to use type 1, which is clear text passwords. But you can see here the password is Cisco, all lowercase on R1, and the password is Cisco, all uppercase, and passwords are case sensitive. So if we do show IP OSPF interface and specifier interface, nothing here. It's not going to show you what the password is. You'd have to go into the running configuration in that case to see it. And when you're using clear text, it's not that big a deal because it'll show up there. If you're using MD5, it's going to show a hash. That can be a problem. But again, refer to the authentication lesson for more detail on that. But what we're seeing here is simple password authentication is enabled on both sides, so we don't have an authentication type mismatch. What's nice though is we can use that same debug, that debug IP OSPF adjacency, and it's going to tell us what the problem is. In this case, it's going to say it's a mismatched authentication key. Clear text. It's not going to tell us what the password is coming in. We can get that from a packet capture if we'd like, but it's going to tell us, you know what, you guys don't have the same password on both sides. You have the same authentication type, but you need to go ahead and make sure that your passwords actually match. I'm going to skip doing that on the CLI. I think it's pretty self-explanatory, setting up passwords so that they match on both sides. And this is getting to be kind of a long lesson, and we want to get moving on. So let's go ahead and take a look at the next possible mismatch, and that is a stub flag mismatch. And now a stub area, I'm not going to go into what a stub area is, other than to say, you know, it reduces the number of LSAs in an area. There's a lesson on that. Stubs can get pretty gnarly in OSPF. As a matter of fact, I think there's a totally gnarly stubby area type. That's not real, but there's a not so stubby area and some other stuff. So it gets goofy there. Anywho, I'm rambling. What we're looking at here is we're looking at two devices, and R1 is going to be an ABR, or an area border router, and we know this because it has interfaces in area 0 and area 12. What we're going to do here is we're going to make R2 a stub. Basically, this connection between R1 and R2 we're going to set up as a stub. I'm not going to go into the configuration too deep, other than to say that you do that on the ABR, which is R1 in this case, and you have to have R2 agree. It has to say, okay, it has to know that it's a stub, so you have to configure it on that side as well. So that's where you get the stub flag mismatch. The flag is actually part of the OSPF packets going back and forth. So let's dive into this. Alright, so router 1 is going to be our area boundary router. Area border router. Always get them mixed up. It's area border router. I can see it in red in front of me. Anyways, and then R2 is going to be our stub, but it doesn't know that it's a stub yet. So R1 is saying, all right, we want to make area 12 a stub area, but R2 hasn't agreed to that yet. So we do a show IP OSPF on R1, which is the ABR. We will see right here that it is an area border router. R2, we issue the same command. It will not show that because it's not an ABR. So we go down to the area that we're talking about. In this case, it's area 12. On the ABR, it's going to show this is a stub area. It generates a stub default route with a cost of 1. Again, we're not going to go into details about the different types of stubs. We're just going with a plain Jane stub here. The important part is when we issue this command on R2, we don't see that this is a stub area. So this is going to be a problem. This has to match. In order to troubleshoot this, we're going to use the debug IP OSPF events. We could also use hellos. That's actually in the hello that the error will be identified, but we're just going to go with the events here. It's going to give us less output, I believe. Maybe not. Maybe I just captured just a little bit less there. Anywho, either one of them will work. So what we're going to see here is that we're getting a hello from R2 with a mismatched stub transit area option bit. So it's not going to tell you what configuration to put on there for the stub, but it's going to tell you that, you know what, it does not know that it's supposed to be a stub. So we're going to have to go over to R2 and fix that configuration. Okay, so let's get on the CLI here. On R1, if we do a show, let's start out with show IP OSPF. What I'm looking for here is this area 12. You can see here that it has been set as a stub area. And if I look up here, I should be able to see, I'm just going to issue the command again, that we are an area border router here on R1. Pop on over to R2 and issue the show IP OSPF command. I'll let you read through that, but you're not going to see anything that says that we're an ABR. And more importantly, you're going to see that when we look at this area 12, it says nothing about this being a stub area, and that's a problem. So now if I do a show IP OSPF neighbor on R2, you can see that we do not have a neighbor relationship. On R1 though, show IP OSPF neighbor. Whoa. So that's a little different than what we've been seeing before. Generally, if we don't see a neighbor relationship on one side, we don't see anything on the other side. In this case, it's saying it's down. It's not just like R2 where you get no output whatsoever. It's in a down state. So if we go take a look at the log, it doesn't say anything much. It just says that, you know, well, it came up and then I changed it to a stub and then it was forced to reset. So it's in this down state. Disregard that duplicate router ID. That has nothing to do with this. I screwed up again when I reloaded these guys. Actually, it came up with the old config. Anyways, that's way outside the scope of what we need to be talking about here. So let's go ahead and take a look at, well, let's do a show run section router OSPF. I mean, generally that's where you're going to see the problem. You can see here that we have area 12 set as a stub, so we have to do the same thing on the other side. But let's go take a look at our debug. So we want to take a look at the hellos. So now we should be seeing a hello come in, and we do. And I just disabled it with the UAll. And you can see here, we received a hello from R2 with a mismatched stub transit option bit. Doesn't give us a lot of detail, but it does point us in the right direction, saying we need to check our settings as far as stub networks. I'll go ahead and take this and pop over to R2 and do the same thing. Let's see if we get the same message. I would assume so. Maybe not. Okay, so it sent a hello. It should be getting one here pretty quickly. Yep. Okay, so it does. So you get the same message. It's saying mismatched stub transit area option bit. So the stub flag is not set correctly. It has to match on both sides. So in order to fix this, we can go into configuration mode and under the router process, go area 12 stub. And let's see if we get a neighbor relationship here. And we do. So it's full. I'm not going to go into what the difference is between the stub and the non-stub. Like I said, I'll pimp out that lesson. There's a lesson on stubs. It goes quite deep in all the different types of stubs, but just know that this does have to match. That this can come up if you have a stub on one side, you haven't set it to match on the other. So next up is the router ID, and this is a case where a mismatch is actually a good thing. You want to have a unique router ID. So we're going to go back to our simple topology. Everything in area 12, R1 and R2 are talking to each other. But what we're going to do, and we saw this earlier because I messed up, I'm going to set both of these guys to have the same router ID. I'm not going to go through how router IDs are selected on devices. There's a lesson on that. So we're just going to hard set the router IDs. It is good to know how that election process occurs though, because that can come out and bite you in the butt in the real world. And trust me, it happened to me about a year ago. So it's good to know how that election process works. And it's also good to always hard set your router IDs. There are a couple different areas you can look at to get the router ID. You could do a show IP OSPF, and it's one of the first things here. It's going to show you the process, which we don't care about. Those don't have to match, but the router ID needs to be unique. And you can see here on R1 and R2, we have set the router ID to be quad ones on both, so we're going to have some bad juju. You can also do this on the interface level with a show IP OSPF interface and take a look at the router ID. Now, if you've hard set the router ID, which I strongly recommend, you could also take a look at the IP OSPF router process in the running configuration and see what that is hard set to, but we can get it from any of these locations. This one actually is going to be good because iOS has deemed this important enough that you need to fix it, and it's going to keep telling you to fix it over and over again. So if you've got logging enabled, you're going to see an OSPF duplicate router ID error message, and it's going to say OSPF has detected a duplicate IP router ID quad ones from router 2. And generally, if you know how your router ID structure is set up, you can pretty quickly say, ooh, I got to go over to R2 and make sure that that is not quad ones, that should be quad twos. And the best way to do that is to hard set that. And you can do that under the router OSPF process with the router ID command. Set it to quad twos, and we should be good to go. You might be looking at this and going, hey, I thought you had to reset the process whenever you change the router ID. Not when there's a duplicate, because as we'll see, this neighbor relationship will not come up. So the relationship has not been created, the adjacency has not been established. You do not have to reset this. Okay, so here we are in the CLI, and you can see already that the router has started kicking out error messages. Do a show log. We should see this in the log. I didn't clear the log, but it looks like they are generated about every minute or so. So let's go ahead and do a show IP OSPF. We're getting clues all along that we have this messed up. The first line here, you can see here that we have a router process and the ID is quad ones. If we do a show IP OSPF int 00/0, it's going to give us the same thing here. It's going to show us the router ID of all ones. Let's pop on over to R2, show IP OSPF, and it's that first line. You can see here's our problem. We've got quad ones. And if we do a show IP OSPF int 00/0, same thing. This is a couple different ways that you can find this. Depending on how the OSPF router ID has been selected, you may be able to see this from the running configuration. So if we do a show run section router OSPF, OS will be submission here. Come on, baby, think about it. There you go. You can see here that we hard set it, so we've got it hard set to quad ones, and we have the same thing on R1. So in this case, we don't need to do a debug. I suppose that we could do a debug because the router ID is in the OSPF hellos. I bet you that it will catch it in the hellos. Let's just hang tight for just a second, see if that is the case. Sent it. Let's see when we get one here. It'll be within test. Here we go. So it's giving us that same message that we got in the log. So no new information is gleaned, and we pretty much know what we have to do here. So we can either change the router ID on R1 or R2, whichever one, but we have to make one of them different. And we're just going to go ahead and go into configuration mode, go under the router and the OSPF process, set the router ID quad 2s, hit enter, and there we go. It's already been fixed. So we can see the neighbor ID, and if we do a show IP OSPF, that first line shows that we now have a router ID of quad 2s. Now, as long as it's different, we're golden. So if we go ahead, this is what I was talking about, that this might throw you off a little bit. You may have seen this in action. If we go under there and we do the router OSPF 1 and we do a router ID of, and again, go check out the lesson on the router ID, how it's selected and what it actually is. We don't need to have an actual interface that matches this. We can have this be quad 22s, and this is where this comes up. It says reload, which really isn't a great option, or use a clear IP OSPF process command for this to take effect. So we've set this to quad 22s. If we do a show run section or router OSPF, we can see that the router ID is hard set to quad 22s, but if we do a show IP OSPF, you see that it still has the quad 2s. So if I do a clear IP OSPF process, yes sir, now it's going to change. So now if I issue that same show IP OSPF, you can see that the router ID is quad 2s. If I pop over here, if I do a show IP, oh man, I'm losing my typing skills here, not that they were that great beforehand. If I do the show IP OSPF neighbor from R1, you can see that the neighbor ID, which is the router ID of the neighbor, is quad 22. So just so you know that generally is the case. Whenever you change the router ID, you do have to clear the process for that to take effect. But what we were looking at before was that there was no adjacency being established, so you don't have to clear it. There's nothing to clear because it's not coming up. All right, so let's move on. So the network mask mismatch, or the Y or sixth vowel mismatch, because sometimes this is a problem, not always. And our topology is going to be the same. I guess we're rocking area 0. That doesn't really matter. But as you can see here, when we're taking a look at the network mask on here, we're looking at R1, and that has a /30 network mask, and R2 has a /24. Not going to go back into network mask, but just to say here that the reason this works is because the .2 actually is included here, because you can have, with the /30, you can have the 0, the 1, the 2, and then the 3 would be the broadcast. This is either review or confusing the hell out of you, depending on how much you know on network mask. But the reason it works is because we'll see this .2 here, so they don't have to match for layer 3 connectivity, but they have to match for OSPF neighbor relationships in some cases, as we'll see in just a second. The network mask mismatch. Network mask mismatch. Didn't know that was going to be a tongue twister. I haven't seen this in the real world. I have seen this in the CCIE lab preparation, because this is kind of a lesser known issue, and again, something you wouldn't think of, because you do have layer 3 connectivity in this case. This isn't the case where, you know, you've got network mask that's so mangled that you can't ping the other side. In this case, we've got it set up with a /30, and we can see this with the show IP interface and then specify the interface, and you can see it's a /30 on R1 and a /24 on the other side. If you want to take time to go ahead and do your binary math to show that the .2 would be found out the interface F0/0, by all means knock yourself out. Otherwise, you can just believe me that this is going to work. And I actually show you at the bottom here that it pings, and that route is out, that directly connected F0/0 interface. If we do a show IP OSPF interface, it does the same thing, just shows us it's a /30. Now, I got this little tidbit up here. It says network mask represents the network mask of the interface on which OSPF is running. Yeah, thank you. The network mask is checked only on broadcast media. That's correct, and it's incorrect. It's not the media type that's going to be the problem here. We'll see this. Actually, we're not going to see this in the lab because I'm not going to go ahead and set up a fast Ethernet connection. You can do that on your own. It's the OSPF network type and not the media type that affects this, and we'll show that by changing this. In this example on the slide, I have fast Ethernet connections between these two routers. So the interface type, the media type, is broadcast because it's Ethernet. Also, if I would have showed all of this show IP OSPF interface, you would have seen that the network type here is broadcast because that's the default, the OSPF network type for broadcast media. But what I want you to understand is that it's not the media that screws this up. It's the OSPF network type. So we can see here that we have layer 3 connectivity. Let's move on to the next slide. And this is kind of insidious because it is based on the network type, and you may see it in one situation where it's working and in another where it's not, and you don't notice that it's the network type. But anyways, the debug that we're going to use is the IP OSPF Hello, and it will show, because remember that ISPF, I'm sorry, it's getting to be a long lesson here. That OSPF Hello packet, it included the network mask in the Hello packet. So if we do a debug on the Hellos, we can see that there's a mismatched Hello parameters, and we know from earlier in the lesson that the R means received and the C is configured. So here we can see that all the dead timers are fine, but the network mask, we can see that it's configured as a /30. We're on R1 and we're receiving a /24. You can also use a debug IP OSPF event, same type of information. Knock yourself out, choose whichever one you like. And then when we go in and fix this, we change the IP address to a /24 on R1. We can see that the OSPF neighbor relationship is established. So the key to this whole mismatch is knowing when it's going to be a problem, when it's not going to be a problem. Well, it's only going to be a problem, and the easiest way to remember this is on network types that don't have the word point in them. Now, I don't particularly consider a virtual link a network type, so that's, well, we'll get to that. And a loopback can't peer with anything. I suppose shouldn't use the word peer. Cannot form a neighbor relationship and therefore an adjacency with another interface. It's a loopback. So I think that's a special case too. So of the 5 major ones, which are broadcast, non-broadcast, point-to-point, point-to-multipoint, and point-to-multipoint non-broadcast, as long as you know that whenever you hear the word point, that it doesn't require that the masks match. But if it's broadcast or non-broadcast, the network masks have to match. Now that's why you come back to that media type. The default for Ethernet is a broadcast, an IP OSPF broadcast network type. So it seems like it's the media type that's affecting it, and kinda it is, because if you were to put this on a 2 serial links between each other running PPP or HDSL, the default IP OSPF network type would be point-to-point. So it can be a media thing, but because we can change OSPF network types, as we'll see on the CLI, it's actually the IP OSPF network type that affects this. I've said this over and over again. I'm sorry, I'm just trying to hammer this home. So, like I said, broadcast and non-broadcast do require that the network mask be the same on both sides. Anything else, it doesn't require it, or it really doesn't matter. Okay, I'm not going to insult your intelligence by reiterating it's a network type one more time. See what I did there. Here we have R1 and R2 set up with serial interfaces between them. So there's a serial line connecting them, and by default you're going to be running HDSL as your layer 2 protocol there. So if we do a show interfaces 00/0 on both sides, we can see that on R1 we have a /30 and on R2 we have a /24. So we have a network mask mismatch. Now we can still ping, we got layer 3 connectivity. Now when we do a show IP OSPF interface, we can see that both of these are network type point-to-points, which is the default for a serial link running HDSL. We can see that we have the /30 and the /24, same thing that we saw before. But now when we do a show IP OSPF neighbor, we see that it's full, that we do have a neighbor adjacency. Whereas when we were doing this on fast Ethernet, we didn't get that. And the reason was, again, because of the network type. Anything that starts with point, whether it's point-to-point, point-to-multipoint, or point-to-multipoint non-broadcast, does not give a damn about the network mask. You're golden. If you're rocking broadcast or non-broadcast, you're going to have to make those suckers match. So just to hammer this home, that it is the OSPF network type and not the media type, what we've got here is we've got serial interfaces set up. We're running HDSL. by default, we would use a network type point-to-point. But what we're doing here is we're changing it from point-to-point to broadcast. And we do that with the interface IP OSPF network type command. And then we specify broadcast. So we've changed the IP OSPF network type, but the underlying layer 1 and layer 2 are the same. It's a serial line running HDSL. So in this case, we have our /30 and our /24. Now recall that in the last slide, when this was point-to-point, it didn't care. It brought up the adjacency. Unfortunately, it showed the show IP OSPF neighbor, so that's not coming up here. But I am showing the debug here, and the debug does show that it is giving you mismatched hello parameters, and the mask is not matching. So it's keying off of the IP OSPF network type, not the media type. And one last time, well, it won't be the last time, I'll probably bug you because I'm going to do this on the CLI. Anything that starts with point has point in there. Don't worry about it. If it's broadcast or non-broadcast, then yeah, you have to worry about it. And here we are on the CLI. If we do a show IP OSPF into brief, you can see here that we have a serial interface on R1, and we have the same thing on R2, show IP OSPF into brief. If I do a show IP OSPF neighbor, you can see that we do have an adjacency established. If I do a show int 00/0, let's go ahead and just include, the typing gets bad. So we can see here that our IP address on R2 is 10.1.12.1/24. If we do the same thing over on R1, you can see that's a /30, but we do have a full adjacency. So let's go ahead and take a look at the OSPF interface 00/0, and we'll look at the whole thing here. We can see here that the network type is point-to-point. And if we go and do the same thing on R2, we should see the same thing. And we do. So remember what I told you, that if it's a point, if the word point is in there, it doesn't matter. It won't care about the network mask not being the same. So let's go ahead and make this interesting and go under the interface, and we will change the OSPF network type to broadcast. And I'll do the same thing over on R1. All right, so now if we do a show IP OSPF neighbor, we don't have an output. Do a show IP OSPF interface 00/0, we can see here now that our network type is broadcast because we just changed it. And I'll spare you the verification on R2 because you saw me do it. So let's go ahead and take a look at the log first. You'll see it. I didn't clear the log, but all right, you'll have to trust me here. It doesn't scream at you and tell you. You can see here what the messages have been, but it doesn't scream at you. So let's go ahead and do a debug IP OSPF hello. And we shouldn't have to wait more than 10 seconds, and we didn't. Let's shut it off. And here we can see we have mismatched hello parameters from R2. We are receiving a /24. We are configured for a /30. So again, this is kind of a subtle one, and it's weird because it only affects certain OSPF network types, not the media type. So this one could come and bite you in the butt because it would work in certain situations and not in the other, and it's not really that well publicized. So again, keep in your mind anything that says point, doesn't worry about the network mask. If it's broadcast, it has the word broadcast in it, whether it's broadcast or non-broadcast, it does, and you will have to match up those network masks. Okay, we're in the home stretch here. This is the last one, and unfortunately I've saved probably the most confusing one for last, and that is the compatible OSPF network types. Now there is a separate lesson based on this, and it goes through all the different types and the compatibilities between them, why they're compatible and why they're not compatible. We're going to be going at a 30,000 foot view here. I would strongly suggest you go hit that video. Well, that one does go pretty deep. You might be able to just get what you need here. This is more of a lab type thing, and this comes up a lot in the CCIE lab prep materials because it can be tricky. In the real world, you're not going to get a lot of this because in the real world, you're just going to set both sides of the link to the same damn network type and not worry about playing around with OSPF to just get compatible ones. If it's the same on both sides, that's fully compatible, and that's all you really need. So Let's, well, we can take a look at our topology such as it is. Same basic topology. We're in area 12. We've got the links. We don't have our network mask mismatch anymore. We're good to go. So what we're going to do here is we're going to start messing with the IP OSPF network types on each side. So as we just saw on the CLI when we were doing the network mask mismatch, you saw that you can go under an interface and you can change its OSPF network type with the IP OSPF network command and then specify a network type. And there's basically 5 different ones. There's broadcast, non-broadcast, point-to-point, point-to-multipoint, and point-to-multipoint non-broadcast. And there are separate lessons on each of those and where you would want to use them. In the real world, you're going to decide what type of OSPF network type you're going to use based on your needs, and you're going to implement that. What you won't do, because there's no good reason to do this, is set up one type on one side and another type on the other side. You'll just make a match, let them do the job that they were built to do. You can do this, though, because they don't have to match, they just have to be compatible. And what does compatibility mean in an OSPF context? Well, it simply means that they either agree to use a designated router or they don't. Any network type that uses a designated router is compatible, and there's only 2 that are using DRs, and that is broadcast and non-broadcast, which is easy to remember because those are the guys that were affected by the network mask. Anything with a point in it, like I said before, you don't have to worry about it. It doesn't use a designated router. So those 3, the point-to-point, point-to-multipoint, and point-to-multipoint broadcast are compatible. So compatibility comes down to whether or not you need to use a designated router. So what that means is you can have one side of your link be set to broadcast as the OSPF network type and the other side set to non-broadcast. And with a couple of tweaks, you can make this work. And the biggest tweak, and that's what I show down here, is that you have to remember that you still have to have your hello parameters matched. So in that case, you do have to have your IP OSPF timers match, the dead timer and the hello timer. Different network types have different defaults, so you may have to change those to get those to work together. As we just saw with the network mask mismatch, that can get thrown in there, but really you're not going to be able to dig your way out of that because you'll have to make a match. You can't use a point-to-point, which doesn't care about the network mask, with a broadcast, which does, and then try and fix them that way. You'd have to go ahead and make sure that you had your network mask consistent on either side of the link. Again, just to hammer this home, in the real world, you're not going to do this. There's no design that I can think of where this is optimal. This comes up a lot in the CCIE lab, as well as it could come up in your CCNP, just to show you that you could make these guys work. It's like making cats and dogs live together. It can happen. It's probably not for the best, and why the hell would you want to do it other than to be sadistic? So I guess one takeaway here is that to never say, oh, you can't have mismatched OSPF network types, because you can. You can't have mismatched OSPF network types that are not compatible. That's a mouthful. Anyways, let's go ahead and take a look at this. So on R1, we've got it set to the network type of non-broadcast, and on R2, we have it set to broadcast. Now, both of these network types utilize a designated router. So in this case, they are compatible. But remember that second part I said that you want to make sure that all your other parameters are matching so you can have these guys come up. Non-broadcast has a default hello timer of 30 seconds, and the dead timer is 4 times that, so 120 seconds. Whereas broadcast has relatively fast timers, which is hellos of every 10 seconds, and then a dead timer of 40 seconds. So this neighbor relationship will not come up. Even though these are compatible network types, you have to go ahead and tweak the timers first. So in this case, I would probably suggest going on R1 and setting the hello timer to 10 seconds. It'll automatically set the dead timer to 4 times that, and then you should get a neighbor relationship. So in this case, we have compatible OSPF network types, and like I said, you're going to have to tweak those timers. Here, we're just doing what we did earlier here, one of the first mismatches we saw, which was the timer mismatches. So we're going to use our debug IP OSPF events, and we see that we have the dead and hello timers are mismatched. So if we adjust the timers on one side to match the other, then just like I said in the last slide, all we have to do is go ahead and put the hello timer, the hello interval to 10 seconds. It's automatically going to set the dead interval to 4 times that, or 40 seconds. So now they match. So now you have cats and dogs living together. You have a neighbor relationship and an adjacency actually between R1 and R2, although R1 is running broadcast on its interface as its OSPF network type, and R2 is running non-broadcast. So you just made yourself a Liger. Good job. Again, I can't think of a situation or scenario in real life where this would be optimal. In this case, just set them both to whatever you want to use. You can set them both to broadcast or non-broadcast, whichever you want to use. It doesn't make any sense to do this. So now here's the one that will make you go weak at the knees, cry, pull out your hair. This is incompatible network type. So we learned that broadcast and non-broadcast are compatible. Point to point is compatible with anything with a point in it. So it's kind of easy to remember, you know, if it's got broadcast in it, then it's compatible. If it's got point in it, then it's compatible, but they're not compatible with each other. So here we see R1 has broadcast, and we see here the network type is broadcast. Note that state waiting. What that is waiting is the designated router slash backup designated router, and I've got a lesson on this, election period. Because remember, broadcast requires a designated router. So at this point, it's saying, oh, I need to elect a designated router. Point to point, on the other hand, it doesn't have this waiting state because it doesn't care. It doesn't use a designated router. So it's like, all right, I'm point to point. That's all I need. So there's no designated router on this network, and, well, no BDR. And the no backup designated router isn't a stumbling block. It depends on the number of devices and who you want to have elected. But anywho, different lesson. The hello timers are matching, so let's see what happens. So we do a show IP OSPF neighbor on R1 side and on R2, and what the hell, didn't I just tell you that these guys are non-compatible? Obviously I've lied because, like I said many times in this lesson, full is golden. One slight difference here. R1 says full designated router, so it thinks that R2 is a designated router, whereas R2, it says I'm full and I don't use a designated router, so I don't give a crap. So is this working? It sure looks like it. And the answer to that is no. And this is tricky because it sure looks like it from all of our show commands. It sure looked like this was working. But all right, sorry about that, some quick editing. We should see R2's loopback, which is a quad 2's in R1's routing table, and R1's loopback, which is a quad 1's in R2's loopback in R2's routing table. When we issue the show IP route OSPF, which that command shows you all the routes are learned via OSPF, we get nothing. When we do a show IP route, we see that the only routes that we have are connected. So this is that case where you have a neighbor relationship, but you don't have an adjacency. And this one is ugly because it does not look like it's broken. It looks like it's working. And really the only way to figure that out is by taking a look at the routes and knowing that you should be seeing routes from that other router and you're not getting them. So as I put down here, this is probably the most frustrating and difficult mismatch to troubleshoot because it appears everything is working. And you will see this time and time again in CCIE lab workbooks because this is such a mind fuck. It's just, it looks like it's working, especially when you've got a CCIE lab and you've got all these routers and all these tons of routes, and you might just not be getting a couple of routes from one neighbor because of this, and you don't notice it, and you fail your lab and you're like, oh, what the hell happened? And you cry, and that's why daddy drinks. So in the real world, you're going to want to be aware of this possibility because, again, this sure looks like it's working, but it's not. Again, anytime that you have mismatched OSPF network types, regardless of whether they're compatible or not in the real world, you need to find out why that is. Generally, it's not I'm guessing that it's somebody messing around or misconfigured it or whatever. I'm guessing that, and I could be wrong, but I can't think anything off the top of my head. It's not an optimized design. So while these network types are compatible, the best way to go is just match them on both sides. And I'm going to spare you the CLI on this one. There is a separate lesson that goes into this really deep. Like I said, this is more of a CCIE lab type thing in the real world, and I'm sure you're sick of hearing this. Just match the damn OSPF network types and leave it at that. All right, this is a long lesson. I'm sure that you're very, very happy to see the summary slide. In order for an OSPF neighbor relationship and consequently an OSPF adjacency, remember those are two different things. We explained the difference between those. To form, there's a number of values that must match between potential neighbors, and we took a look at those today. And the ones that have to match are the hello interval and the RouterDeadInterval, as well as the area. The authentication must match in both method and password. And then if you're running a stub network, you have to make sure that all the routers that are supposed to be stubs know that they're stubs, and that's a stub flag. So if you have a mismatch, that will break your connection. And then MTU as well. That one can be kind of hard to troubleshoot because that's separate from OSPF. That's, it's not really an OSPF centric setting. And then furthermore, there's things that must be compatible, and We just came out of that mess, and I have a lesson on that completely explores the compatibility between the OSPF network types. I guess the takeaway from here is that don't fall trap to the whole, oh, the network types must match, because technically they don't. They must be compatible. And if you remember back, if it says broadcast in it, then it's compatible with anything else that says broadcast in it. If it says point in it, compatible with anything else that says point in it, because the compatibility is based on whether or not the network types need to use a DR or not. So that's a separator. And like I said, there's a whole nother lesson on that goes a lot deeper into that. As far as mismatches that we do like mismatched router IDs because we do not want those to be the same. Luckily for us, that's one of the few of these mismatches that will have iOS shouting at you and saying, hey, 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 you need to change this. It's the same as your neighbor. And then the sneaky one, the one that has to match sometimes, is the network mask. And as we saw here, kind of the same rule as the compatibility between network types. If it says broadcast in it, which is broadcast or non-broadcast in it, yes, the network mask does have to match. If it says point, and again, we're talking about the IP OSPF network types, it's not the media type. If it says point, then it doesn't care. It doesn't have to match. You can have different masks on, well, as long as you can reach either layer 3, you can have different subnet masks on those interfaces. So that's going to wrap it up. Thanks for sticking with me through this pretty long lesson here. There's a lot of information in here. This is actually going to help you out quite a bit in quote unquote the real world, as well as in exams, and specifically the CCIE lab exam. This will help out quite a bit. You'll probably run into a lot of these out in the real world, and it's very good to be aware of the different types of mismatches and how to troubleshoot them. And we went through a bunch of debug stuff. Oh, I owe you guys a slide on that. I'm just going to make that a separate lesson, and I'm going to actually point to that in the show notes here on the packetlab.com site so that you can see that. Basically, it's showing you how to restrict your debugging to an interface rather than having all the interfaces be debugged. That'll actually help you out. Anyways, it's been a long one. Let's get going here. So thanks once again for joining me in the Packet Lab. As always, I hope this helps